go over today. And part of the reason why I want to just talk about these in particular is because you're going to have two different types of final exam. The first final exam that you have is what we call a concept inventory. And the structure of that concept inventory is that it asks you multiple choice questions to really get at whether or not you understand a concept thoroughly or if you still have misconceptions about that topic. So that is an individual assessment. Our goal when we do that assessment is to think about what it is that you might need additional support with as you go into the second semester of general chemistry, right? And then what are areas where you've demonstrated that you have competency or an understanding that's pretty thorough of that topic. The second part of your final exam is a collaborative exam similar to what you have worked on for exam 2 or exam 3. So it's not an oral exam. It'll actually be something that you're going to turn in and then receive a score back for in terms of your written work. But the idea is that you could work collaboratively with your fellow scientists. So the goal behind working on these problems is that you're going to be able to work together. They're also going to be problems that are integrated. What I mean by that is it's going to typically ask you to do more than one skill or apply more than one area of knowledge. So if you think about that, you're like, well, maybe that's where I have to use stoichiometry and balancing an equation and my knowledge of gas laws in terms of Dalton's law to be able to make sense of a problem. And so those types of problems take a little bit more time to do. So essentially you'll have a long window in which you can work on that second part of your final exam, and you can work together, you can work independently, you can work in pairs. The whole point though is that you're able to integrate and really apply your knowledge. So we're going to spend a little bit of time today reviewing different types of problems that you will see on both of those parts, and I'll try to be really clear about what would apply for part 1 of your final exam versus what would apply for part 2. So just to be very clear, your final exams are cumulative. Cumulative means that we cover everything from the very first day that we had class, ever so very long ago, which was chapter 1, all the way up through chapter 10. And so if you think about that, that's actually a fair amount of material that you're going to be responsible for. So hopefully you're taking some time now to do some review. So let's talk about what that would look like. Our focus today, again, is to make sure that you know that questions are welcome. So if there's something that we're talking about and I'm going too fast, right, or you need clarification on a concept, just put a note in the chat, or by all means unmute yourself and ask a question. It's always welcome. I believe your classmates are always thankful for it, and I appreciate you asking clarifying questions too. All right. You are going to be expected to be able to execute all 4 of these practices on both parts of your final exam. If you're not sure what these entail, right, some good examples would be writing claim evidence reasoning statements, being able to interpret diagrams or read tables, being able to construct dimensional analysis or conduct calculations, and then being able to think about information and determine what are the most relevant variables or pieces of data from a problem in order to be able to create a solution. Several of you have asked for a quick overview of hybridization. So that's where we're going to start today. We're going to take a look at this molecule, which is oseltamivir. It's actually an antiviral drug, really interesting chemistry that it's able to do in human beings. And it's one of the candidates that's currently being evaluated as medication that could be used to help treat COVID-19. So when we look at a molecule like this and we're asked to assign hybridization, what we're being asked to do is look at each individual atom in this molecule. And specifically, we're being asked to look at the number of electron groups that each atom has. Remember, electron groups can be a lone pair, it can be a single bond, could be a double bond, could be a triple bond. Anything that is a group of electrons constitutes a group. We also sometimes refer to this as a steric number. So in order to be able to solve this problem, there are a couple of things that we need to do. The first thing that we need to do is to draw what is missing. So these are molecules that are often drawn in a line angle form for the sake of expediency. Like any model, there are benefits, i.e. being able to draw it quickly, and there are also limitations. The limitation in this case is there's some information that's missing. And so being an astute chemist, you need to know what information is missing and when you might need to draw it in order to make sense of how to solve a problem. And here, there are three things that we're going to draw in. We're going to draw in our hydrogen bonds. Those are really important because they're going to represent electron groups that if we don't draw them in, we'll feel like they're missing. Also, they're important because that's how we typically complete the octet for carbon molecules. If you would like, you are welcome to draw in your carbons. Any bend or point of a line represents a carbon. The last piece that we need to draw in are our lone pairs. And so you'll notice that there are bonding patterns for oxygen and nitrogen that we need to observe. Another way that you can think about that is also completing the octet for these heteroatoms. So heteroatoms are atoms like oxygen or nitrogen, anything pretty much other than carbon that's a nonmetal, that where we might need to provide additional electrons in order to satisfy the octet rule. So, a couple of things then. When we're counting hybridization, all single bonds to hydrogen are considered s, right? So it's not a hybrid orbital, it's just a direct overlap of the s orbital. Then, when we're looking at each individual atom that's not a hydrogen, we need to organize by the type of hybridization and the number. So if you recall, we have 5 different types of hybridization that we need to consider. There's sp3d2, when an atom has 6 electron groups. There's sp3d, when an atom has 5 electron groups. And then there's sp3, when an atom has 4 electron groups. sp2, when an atom has 3 electron groups. And sp, when an atom has 2 electron groups. Now, here's the lovely part about this. Once you practice this, you'll get faster at being able to recognize whether an atom is sp3, for example, or sp2. The way that I think about this is I look at my carbons, and almost always, unless it's a double bond, my carbon is going to be sp3. That's because carbon typically has 4 bonds. If I have a carbon that is part of a double bond, then I'm going to have 3 electron groups. The double bond constitutes 1 electron group, and then I have 2 single bonds. Carbon still has a complete octet, but now instead of being sp3, now it's going to be sp2 because it has only 3 electron groups. So your goal when you're assigning hybridization is to look at each individual atom. If it helps, you can number them, right? That's one of the ways that I check to make sure that I've accounted for all of my atoms. Or one of the other strategies that I've actually seen folks successfully use is to talk about the different types. So they'll count, for example, the number of carbon-carbon bonds. They'll count, for example, the number of carbon-carbon double bonds. They'll count, for example, the number of carbon-hydrogen bonds. And then they'll go through and assign hybridization that way. There's lots of flexibility in terms of how you answer this problem. And you don't necessarily have to draw everything out if you know it's there. But if you're not sure, then drawing out is one of the best ways, I think, to solve these types of problems. Okay. There are lots of other examples where you could assign hybridization, and I can guarantee that you will see at least one of these types of problems on your final exam part 1.
Dr. Corey?
Yeah, Heba.
So I have a question about carbon.
Yep.
So carbon always tend to create bonds, like it never has like lone pairs on it?
Rarely, very, very rarely does carbon have lone pairs.
Okay, thank you.
Yeah, not a problem. Great question. When you get to organic chemistry, you will start to see carbon atoms that have less than 4 bonds or lone pairs. My guess is that you typically won't see that until then, but it is, and there are times when carbon can have either lone pairs or less than an octet. Great question, Heba. Thank you for asking. This was another example of a problem that I think required some integration. And so it's a good example from exam 3 of a type of problem that you should expect to see on your final exam part 2. So this is a problem that starts out asking about stoichiometry, but then it asks you to make sense of a couple of other pieces of information. So it says a silver nitrate solution reacts with a metal chloride. A silver nitrate solution reacts with a metal chloride, which reacts to give a precipitate of silver chloride. When a solution containing 0.950 grams of metal chloride is made to react with silver nitrate, 2.87 grams of silver chloride are formed. Identify the metal. This is a great example of a problem where you want to stop or pause for a moment and think about the solution and maybe the map of how you would get there. So for example, you're given 2 different pieces of information in this problem. You're given the mass of the metal chloride, and you're also given the mass of your silver chloride. And you're asked to be able to identify the metal. Metal in this case is just represented by the letter M. So in order to solve this problem, we're going to do a couple of things. The first thing we're going to do is check our balanced equation. You never know if an equation is correctly balanced, and it's always good practice to check. You're checking both for the coefficients as well as the subscripts to make sure that they make sense. Then your next step in this case is to start with the information that you have available to you. Sometimes if you're not sure where to start, it's actually not a bad idea simply to look at the information and see what else you can calculate based on that information. So here we're going to find our moles of AgCl. We're given the mass, 2.87 grams, and we can calculate the molar mass of AgCl by looking at our periodic table. Once we sum the individual molar masses of silver and chloride to get our overall molar mass of AgCl, and we divide our mass in grams by the value of our molar mass, then we're able to cancel the units for grams and find the moles of AgCl. From there, we're going to look at our balanced equation because we're not really interested in AgCl as much as we're interested in the metal chloride. So then we're going to use our moles of AgCl and what we refer to as the molar ratio from our balanced equation to find the moles of our metal chloride. Once we have the moles of our metal chloride, we can actually determine its molar mass because in the problem, we're given the grams of the metal chloride. We have the moles of the metal chloride. And so if I recall that the unit for molar mass is grams per mole, I can divide the grams by the moles that I've calculated. And that's going to give me a specific molar mass. Molar mass in this case is 94.88 grams per mole. But I have to be attentive to detail. In this case, my metal chloride doesn't have just the metal, it also has 2 chloride atoms. So in this case, I need to subtract the molar mass of chloride, multiplied by 2 because there are 2 of them, to determine the molar mass of the metal by itself. In this case, the molar mass of the metal is 23.97 grams per mole. And when I look at my periodic table, the closest match to that molar mass is magnesium. Now, there's another way that you could have set up this problem, and I think it's really important at this point to say that there are multiple ways typically to solve these types of problems, and the structure, how you set up solving that problem, is in many ways up to you. So for example, if you wanted to condense your initial calculations, the first 3 steps that we did, you could do so, right, by converting your grams to moles, your moles to moles of your metal chloride, and then do the second part of the calculation. So if that's something that you feel more comfortable setting up, that makes more sense to you, that's fine. If you're someone where you're more comfortable doing it as individual steps and justifying your steps, that's fine too. What I'm hoping that you'll do is for part 2 of your final exam, that you show your work to justify, right? Your work being your evidence to justify your claim. So as long as your work helps me to understand how you arrived at an answer, that's really what's most important for me, and the way I can give you the most valuable feedback. I want to take a moment and talk about the fact that when we look at types of reactions, it's really important that we apply some of our savvy chemical knowledge. So for example, there was a problem on one of the versions of the exam that asked you to balance the equation and then assign oxidation states and determine which atom is oxidized and which atom is reduced in the following equation. Well, not all reactions are oxidation reduction reactions. And so sometimes when we're evaluating evidence, we may decide that based on the evidence that we have, such a reaction cannot take place, or that would not be an appropriate way to describe that reaction. And so when we evaluate the evidence, sometimes saying no is just as important as saying yes. Let me show you an example. So we have lead nitrate and potassium bromide going to form lead bromide and potassium nitrate. Now notice, for this problem, the very first thing that you have to do is balance the equation. And it's critical here that you're balancing that equation both in terms of the coefficients as well as the subscripts. And if you're not sure, right, there are some tools that are available to you: your solubility rules, your list of atoms, your list of ions. Those are all great places where, if you're not sure, is a good place to start. So when we balance our equation, we have lead nitrate. Notice there's a subscript 2 for our nitrate, which makes sense because we know that nitrate is a polyatomic ion that has a -1 charge. We have to put a 2 in front of our potassium bromide because if we look on the right-hand side of the equation, right, in order to balance our lead, which is going to have a 2+ charge, and we know that because we look at our common ions and we look at the charge for lead. And bromide, we know, has only a -1 charge, so we need to add the subscript 2 so that it's PbBr2, where the 2 is a subscript. And then in order to balance, right, our nitrate on the left-hand side, we also have to add a 2 in front of our potassium nitrate. And so if we go through and check, we have 1 lead on each side, we have 2 nitrates on each side, we have 2 potassium on each side, and we have 2 bromide on each side. And so now we're confident that our reaction is balanced. Then the problem says we need to assign oxidation states. The key here is that you recognize that there are rules associated with assigning oxidation states. Those rules, if you're not familiar with them, are an available handout. You can also look them up on the internet. I think it's a good example of something that by the time you're done practicing this for the second semester of general chemistry, you'll be pretty familiar with how to assign the oxidation states, and you probably won't need to refer to that sheet. But if that's something where you're not comfortable yet, then I highly recommend that you have the rules of oxidation states available for your final exam. That's a great resource to have handy if you don't know how to do that off the top of your head. So when we assign oxidation states, we know that for any of our ions, the charge of that ion is typically the same as its oxidation state. There is a list of priorities, and so sometimes if we have a polyatomic ion, the charge is something that is determined by which atom has the highest priority. So for example, if we're looking at nitrate, that's the case. The charge for oxygen is established because it has higher priority than the nitrogen. So we know that oxygens are always -2, except for when it's an oxygen in peroxides. Then it's a -1. So in this case, oxygen is -2. This is something where when we're going to solve then for the oxidation state of our nitrogen, we have to take into account the charge on oxygen, the number of oxygens, as well as the overall charge on the molecule. We're going to set up an algebraic equation where we're solving for our unknown. Unknown in this case is nitrogen. What is known is the number of oxygens and its charge. So we have 3 oxygens and a -2. And we set this equal to the overall charge on our polyatomic ion, which in this case is -1. Then we go through the process of solving for nitrogen, our unknown variable. Now, if you don't have a polyatomic ion and you just have the ion by itself, it's pretty easy to assign its oxidation state. So in the case of potassium, its oxidation state is the same as its charge, +1. In the case of bromide, its oxidation state is the same as its charge, -1. When we get to PbBr2, again, our charge is the same. It's +2 because our ion Pb has a +2 charge. And our bromide is also -1. Note we have 2 of those. And again, we go through the same process to assign the oxidation state for potassium and the oxidation state for nitrogen and oxygen. What I want you to notice is that if you look at the left-hand side of this equation and you look at the right-hand side of this equation, our oxidation states are not changing. If there is no change in oxidation state, then this reaction is not redox. It's actually, in this case, a displacement reaction. Sometimes we can have reactions that are displacement reactions and oxidation reduction is taking place. Sometimes there's no change in our oxidation state, and so it's just a displacement reaction. This is where it's really important that you use critical thinking to determine whether or not an oxidation and reduction reaction is taking place. So in summary, if there is no change in oxidation state, then there's no redox that has occurred. This is a type of problem that I expect you to be able to answer on part 1 of your final exam. We've talked, not necessarily recently, about limiting reagents, but because several of you have requested this as a review problem, and because it was quite a long time ago, actually pre-COVID-19 even, it's useful, I think, to do just a quick review of this type of problem because you are guaranteed to see this on both part 1 and likely part 2 of your final exam. The problem says the equation for the reduction of iron ore in a blast furnace is given below. How many kilograms of iron can be produced by the reaction of 7 kilograms of iron oxide and 3 kilograms of CO? How many kilograms of the excess reagent remains after the reaction has ceased? Okay, so if you're thinking about this type of reaction, the first thing you're going to do is check to see whether or not you have a balanced equation. Always, always, always check to see if you have a balanced equation. It's the best place to start a problem typically. So we're going to check, make sure that we have the same on the left for each atom that we have on the right. So in this case, we have 2 irons on the left, we have 2 irons on the right. In this case, we have 3 carbons on the left, we have 3 carbons on the right. And then on the left, we have 6 oxygens. Make sure that you count all of the oxygens that are available because we actually have oxygens in both of our molecules. And because we have a coefficient in front of our carbon dioxide and we have the subscript 2, 3 times 2 means we also have 6 oxygens on the right-hand side, and so our equation is balanced. In order to solve limiting reagent problems, the first thing that you're going to do is think about the units that you're given with respect to the mass. Typically, when you're solving limiting reagent problems, you want your units to be in grams. This information was given in kilograms in the problem, so we do a simple conversion to convert our kilograms to grams. Make sure that when you're doing this conversion, you set it up in the right order. Sometimes I've noticed that folks will flip-flop and they'll say, for example, that there are 1,000 kilograms in 1 gram. That is not true. Make sure that you're using the correct conversion when you're converting from kilograms to grams. In this case, the correct conversion is 1 kilogram is equal to 1,000 grams. So once we've solved for our starting materials in terms of the number of grams, then we're going to convert the number of grams to moles. The reason why we do this is because each of the molecules that are our starting material have a different molecular weight or molar mass. If we want to be able to accurately compare the amounts that we have in order to find our products, we have to convert to moles. In order to do that, we have to find the molecular weight of iron oxide and the molecular weight of carbon monoxide, or CO. Once we have those molecular weights or molar masses, we can convert our grams to moles. This is important because we need to know the moles of our starting material in order to be able to use the molar ratio from our balanced equation to be able to find the moles of our product. If we're thinking about how we find moles of product, we take the moles that we calculated from our grams and we use the molar ratio. In this case, we look at our balanced equation to determine how many moles of Fe2O3, our starting material, for example, are necessary to produce 2 moles of iron. This information comes from our balanced equation. Once we have converted each of the starting materials to the amount of iron that they would each make respectively, then we do a comparison. Whichever number is the smallest, keywords smallest, that amount in moles is our theoretical yield, and the reagent, right, that makes that theoretical yield is our limiting reagent. So in this case, our limiting reagent is CO, because I make 71.4033 moles of iron for the amount of carbon monoxide that I start with, which means that I'm going to have excess iron oxide left over if I were to react these two together. So in order to figure out the amount of iron that I can make, I'm going to take the moles that I generated of Fe and multiply by the molar mass of iron. That's going to give me an amount in grams. If I'm asked for it, I can easily convert that amount in grams to kilograms. And of course, you're paying attention to sig figs and units. But we're not done, because this problem had a part B. It asked us to also find the amount that remained of our iron oxide. There are several different ways that you can determine the amount of iron oxide that gets consumed. This one is the approach that I favor, right? I say 1:3 as x is to 107.105, and that's how I get 35.702. But you could also go back to your original calculations, determine the amount of iron oxide used to generate the iron, and then subtract that from the amount of moles that you had to start with. Once you determine your remaining mass, you're going to be able to then determine how much is left over. So in order to do that, we're going to find the number of moles. We're going to convert the number of moles to grams, and that's going to give us the amount that gets consumed. If we know the amount that gets consumed to make our product, we can subtract that from the initial amount that we had available. That amount, again, is given in grams. I can easily convert it to kilograms, which tells me the amount of my iron oxide that's remaining. This is what we refer to as the reagent that is in excess. If you want additional practice with limiting reagent problems, there are a variety of practice problems to try, so please don't hesitate if this process is something that you feel you need just a little bit more practice with. If you're good to go, then let's move on.
I had a quick question.
Go for it.
How did you get the 35.702?
There's actually several different ways that you can do that. So one of the ways I think that's probably most straightforward is to go back up to the original amounts that you determined, right? So you have 107.105 moles of CO. And so you can actually use your balanced equation to figure out how many moles of Fe2O3 you would need based on this equation, right? So 107.105, find the molar ratio. So in this case, right, for every 3 CO, that would be in your denominator. In your numerator, I have 1 Fe2O3. So essentially, if you take your 107.105 and divide by 3, that gets you your 35.7.
Got it. Thank you.
You're welcome. Okay. Let's think about polarity. This was a question that several of you brought up as you were working through exam 3. And we're going to do a little bit of review of resonance just because it never hurts. So we're going to draw Lewis structures for the molecules that are represented below. I went ahead and I drew the Lewis structure for bicarbonate here, but I also drew another Lewis structure because I think it's important that you know that both of these are acceptable Lewis structures. If you drew the one that's in the box, great. If you drew the one that's below the box, equally great. There's no wrong Lewis structure as long as you meet the requirement of satisfying the number of valence electrons, satisfying the overall net charge if there is one for that molecule. Notice when we're drawing Lewis structures, we always include our lone pairs. Lone pairs are essential. You cannot neglect them. They need to be present in your molecule, just like formal charge on individual atoms. Just like if there's an overall net charge, you need the brackets and that charge on the outside upper right hand. When we're thinking about polarity, one of the things we actually want to think about is the way we represent polarity. So for example, we're looking at the Lewis structure for HSCN, and this is another example where you could draw multiple Lewis structures that are correct. In fact, I have not even drawn all of them here. I've just drawn 2 of them. And you can see the movement of electrons that make that possible. And then the last example is our CH3SH. This is a critical moment where you might need to use, say for example, a wedge and a dash in order to show that this is a 3-dimensional molecule. So if we're thinking then about polarity, the question that came up on the exam was, on the basis of the Lewis structures drawn above, answer the following questions about the particular molecule indicated. So the first question is HSCN a polar molecule? Next question is, what is the electron geometry? And then what is molecular geometry? So let's take that first question 1, right? So if we think about 1, we're looking at the direction that we draw our bond dipoles. So hydrogen is less electronegative than sulfur. And so the arrow points towards the sulfur, where the back end of the arrow or the hatch of the arrow is on the H. The point is towards the S. Same thing is true for carbon with respect to nitrogen. Nitrogen is more polar. So the back end of the arrow is on the carbon, the point of the arrow is on the nitrogen. So if we think about adding up these 2 vectors, is actually what they're typically referred to, our net arrow points towards the right. And so because there is no symmetry in this molecule that cancels out those bond dipoles, I have a net overall polar molecule. Let's think about 2. So what is the electron geometry for C in the best Lewis structure for HCO3 minus? So in this case, my carbon is going to be trigonal planar. The reason I know that is because there are 3 electron groups. If I need to, I can go back up to my Lewis structure to be able to count those electron groups. What about molecular geometry for CH3SH? This one's tricky because there's actually 2 central atoms. And what you're going to notice is, as we study more complex molecules, sometimes you're going to have more than 1 central atom. So in the case of the carbon, it is bonded to 4 electron groups. And so it's going to be tetrahedral, both for its electron geometry and its molecular geometry, because there are no lone pairs. But for sulfur, while it is tetrahedral because there are 4 electron groups, it's going to be bent because the sulfur has 2 bonds and 2 lone pairs. Again, if you're thinking about exam 1, your final exam part 1, and your final exam part 2, you're going to want to have your electron and molecular geometry reference sheets available because you're definitely going to see these types of questions. Let's take a minute and think about the way that gas laws problems can sometimes ask us to do more than one thing in order to solve that problem. So, for example, if you were to place 3 moles of nitrogen gas and 4 moles of oxygen gas in a 35-liter container at 25 degrees Celsius, what will the pressure of the resulting mixture of gases be? So this is a type of problem that actually requires you to draw on multiple pieces of information in order to solve the problem. The first question you should always ask yourself is that if you're told that it's gases, you want to ask if you have everything in the correct units. So for example, in this case, I know that I'm given my temperature in degrees Celsius, and I know that I need to convert that to Kelvin. If my volume, say for example, was given in milliliters, I might need to convert it to liters. In this case, I'm already given liters, so I know that I'm good to go. And then it never hurts to know or have a place where you can reference your gas law constants. You don't have to know these off the top of your head. You just have to know where you can look them up to find them when you need them. So in this case, R is 0.08206 liters times atmospheres per mole Kelvin. Now this is really important because these units are actually going to drive everything else in our calculation. So we know the ideal gas law is PV equals nRT, and we can rearrange that expression to solve for pressure. Before we can substitute everything in though, we need to calculate the total moles, because in the problem we're given 3 moles of nitrogen and 4 moles of oxygen, and we know that if we're trying to find pressure, we have to account for the presence of both gases. Then I'm going to substitute in my value of moles, my R or my gas law constant, my temperature in Kelvin, and in my denominator, my volume in liters. I can cancel my units to ensure that I have the correct unit for my final answer, and my pressure in this case would be 4.89 atmospheres. Again, I need to be attentive to sig figs. This is a type of problem that you will easily see on part 1 of your final exam, as well as something that could show up on part 2. So being able to navigate between information that's given in terms of variables, what the correct units for those variables are, and then whether or not you need to do conversions in order to be able to use the information are all questions that you're going to be wanting to ask when you approach problems of this type. Similarly to gas laws, when we look at heat capacity problems, we also want to be attentive to the units and the information that is given. Most particularly, we want to make sure that if we're thinking about specific heat and heat capacity, that we're attentive to the units, because that will actually tell us which equation we should be using. In the case of this problem, it says a 19.5 gram sample of methanol at 205.9 Kelvin is mixed with 44.3 grams of methanol at 312.3 Kelvin. Calculate the final temperature of the mixture, assuming no heat is lost to the containers and surroundings. The specific heat of methanol is 2.53 joules per gram Kelvin. Now, this is an example of a problem that has a lot of information in it, so it might be useful to write out your givens. Notice, because you're given your temperature in kelvins and you're given your specific heat in kelvins, in this case, you don't have to do a conversion, but you can easily imagine a scenario where perhaps your temperature is given in degrees Celsius, or your specific heat is given in a different set of units, in which case you might have to think about reconciling or doing a conversion so that you have units that will cancel. When we think about the setup for heat transfer problems, one of the things we're always asking is, where do we put the negative sign? The reason we have a negative sign is because we have heat transfer. There is something that is giving up that heat, and that heat going away or out is what we call an exothermic reaction. The negative sign is actually also something that, as a convention when we're doing the math, allows us to get the correct setup in order to derive the accurate answer. And so we want to be careful to make sure that when we're thinking about our Q's being equal, that we include a negative sign. In this case, the negative sign is the thing that's giving off the heat. And you can actually see that here, right? So our initial temperature is 205.9 for our 19.5 gram sample. This is what we think of as our cool sample. And then 312.3 is our warm sample. And we have 44.3 grams of that. And we put our negative sign in front of the warm sample that's giving off the heat. Then we do our algebraic manipulation where we distribute and we combine like terms. This is a great example of something that can be 1 step, 2 steps, or 4 steps, depending upon how careful you want to be with distributing or using PEMDAS or whatever algebraic rules you use for, say, for example, distributing terms. If you're less likely to make math errors, then you can shorten that and have it be fairly abbreviated. I, though, know that when I'm entering numbers into my calculator, I'm more likely to make a mistake, and so I try to be careful to make sure that I write it out at least 2 ways. When I'm writing out my initial distribution, so 19.5 times my TF and 44.3 times my TF, notice I can cancel my specific heat because they're the same on both sides. That's because I'm pouring methanol into methanol. If I was pouring water into water, that would also cancel. But if I'm pouring, say, for example, metal into water, then I can't cancel those terms and I actually have to include them in my calculation. Once I combine like terms, and what I mean by that is anything that has a TF associated with it, I group those together. Doesn't matter which side I group them on, I just need to get those terms together. And then anything that is a number only term, I also need to group those together. Then I will be able to divide to isolate my variable. In this case, I want to isolate my final temperature. And so I divide both sides by 63.8. My final temperature in this case is 3 sig figs or 280 Kelvin. Notice there are a couple of things that I can do to ensure my success when I solve these types of problems. The first thing I can do is write out all of my givens. If you're not sure where to start, if you're not sure what information you have from the problem, I highly recommend that you write out all of your givens. The next step is that you write out the equation. Now, in this case, you have some choice. You could rearrange your equation to solve for the missing variable. That's always an appropriate choice. Or you can substitute in your values and then solve. In many ways, it's up to you what your preference is as you solve these types of problems. I promised that we would do another example of a Clausius-Clapeyron equation. And part of the reason why it's important that we practice these is because you are guaranteed to see this on either your exam, your final exam part 1, or your final exam part 2. And so it's important that you feel comfortable setting up and walking through this calculation. So the vapor pressure of water is 1 atmosphere at 373 Kelvin. The enthalpy of vaporization is 40.7 kilojoules per mole. We're going to estimate the vapor pressure at 2 different temperatures, 363 and 383 Kelvin respectively. Now, this is a great example of a problem where we're given information and we have to do a little bit of mental sorting. We're actually given 3 temperatures. When we think about our Clausius-Clapeyron equation, it only holds 2. So that means that likely we're going to have to do at least 2 different calculations. If, right, as you're looking at this, you're thinking, I bet you if Corin was tricky, she would give me my pressure in something other than atmospheres and my temperature in something other than Kelvin, or my enthalpy of vaporization in kilojoules per mole rather than joules per mole. You are correct. That is likely something that you are going to see and going to have to make sense of. In this case, because you're given atmospheres and you're given Kelvin, you do not have to convert either of those, but you will have to convert your kilojoules per mole to joules per mole in order to be able to solve the Clausius-Clapeyron equation. So again, we're going to write out the information that we're given. So we know that our pressure is 1 atmosphere and our T1 is 373 Kelvin. If you don't remember the Clausius-Clapeyron equation, that's okay. That's why you have an equation sheet. You're going to want to, though, write the original equation because we have some substitution that we need to do. In this case, we need to be attentive to the units of our gas law constant. The units in this case are joules per mole Kelvin. The value is 8.3145. Please make sure that you are choosing the correct gas constant when you are solving problems of this type. Notice I also had to convert my kilojoules to joules. So instead of having 40.7 kilojoules, I now have 40,700 joules. Notice I can also simplify my expression on the left-hand side. P2 divided by 1 atmosphere is the same thing as the natural log of P2. So that's one way that I can simplify my expression. On the right-hand side, for me, because I'm always paranoid about entering information into my calculator incorrectly, I actually go ahead and resolve my fractions to decimals, and I write those out. Notice I want to be particularly attentive to this negative sign. It's actually an error that I'm often easily making. I don't want to forget that negative sign. It's present in my equation, right? That's on my equation sheet. And I want to make sure that I include it when I'm writing out my terms here. If that's something where, like me, you are prone to making that mistake, then it's always helpful to have a friendly voice remind you to go back and double check that. Once we've written out or simplified our terms, then we can go through and use E to resolve our natural log. So E to the power of the natural log is what will get P2 by itself. Once we do E, and again, make sure you're being attentive to whether or not you still have a sign that you have to contend with, you're going to get your P2. And so in this case, right, I know that I need 2 sig figs. So if I were to resolve this in terms of the correct number of sig figs, this would need to be P2 is equal to 0.70 atmosphere, because in my problem, right, I'm given 2 sig figs for my 1 atmosphere. So if I'm thinking about sig figs, I want to make sure that I resolve this and it becomes 0.70 atmospheres. So take a moment and set up solving for 383 Kelvin on your own. If you're not sure how to do this, now's a great time to check your working knowledge. If you're like, that's nice, Corin, but I don't remember that, it's okay. Use this as a guide. Go ahead and do your practice. This is a problem that if you haven't solved it in discussion for the discussion worksheet, you're going to want to go back and practice. If you have, a little bit of extra practice never hurts. If you want to check your answer, go ahead and check the virtual learning plan. I've got a resource for you that actually walks you through the Clausius-Clapeyron equation. So you'll have the opportunity to check your answer to determine whether or not you've set up and solved for P2 correctly. One of the things that I think is valuable, and I'll just yammer on here for a moment while you guys are working on solving this problem, is understanding what vapor pressure actually means. So vapor pressure is the pressure above a liquid, right? It's the pressure of gas. So it's the pressure of something pushing down on a liquid, for example. That's important because sometimes when folks are thinking about boiling, right, they get confused between boiling and vapor pressure. So boiling is the pressure, right, of a molecule in liquid water trying to escape the liquid water. Whereas vapor pressure is the pressure of something in the gas phase pushing down on a liquid or potentially a solid, depending upon what substance you're looking at. Okay, so if you need to, go ahead and check the virtual learning plan. I'll post some additional support for solving Clausius-Clapeyron equations there. The last type of problem that we're going to take a look at is a steppy one. And this is an example of a phase change problem. So this problem has probably 3 different distinct parts that we need to be attentive to. It's a great example of the type of problems in chemistry that are summative. Summative just means that typically when we're solving a problem, we solve different parts of that problem, and then we have to add those parts together. So here's an example. If you had a 50-gram ice cube at 0 degrees Celsius, and you added that to 500 milliliters of tea at 20 degrees Celsius, and you wanted to find the temperature of the tea when the ice cube has just melted. So we need to carefully think about our assumptions here. We're going to assume that no heat is transferred to or from the surroundings, right? That's going to be critical because if you think about it, typically you're going to be transferring some heat. So it's important that when we're thinking about solving these problems, that we think about what assumptions we're making and whether or not those assumptions match with reality. The density of water and iced tea is going to be 1.00 grams per milliliter over the range 0 degrees Celsius to 20 degrees Celsius. It's important to note that density actually of water can vary depending upon the temperature. In this case, we're going to work with the assumption that it's 1.00 grams per milliliter over the temperature range that we specified. And we're also given that the specific heats of liquid water and ice are 4.184 joules per gram degree Celsius and 2.062 joules per gram degree Celsius, respectively, and that the enthalpy of fusion of ice is 6.01 kilojoules per mole. That is a lot of information in a single problem. One of the things that you're going to be practicing, particularly as you transition from Chem 110 to Chem 111, is reading problems, specifically word problems that have a dense amount of information in them. So one of the things you're going to be practicing as a skill is being able to pull out or isolate to be able to identify the most critical information that's found in a problem. That's why writing out your givens is such a good practice, because sometimes you're going to be given multiple pieces of information and you won't need to use all of them at once. You'll be able to use them strategically as you work through solving the problem. Let me show you an example. If we're thinking about phase changes, we know that there are two equations that can apply. There's Q equal to mCs delta T. That's when we're adding heat to something that is in one phase. And then there's Q is equal to N delta H fusion. So this is where if I'm going from, say for example, a solid like ice to a liquid, water, right? I need to calculate the heat of that transformation. So we're going to start with what we know because it's going to be a lot easier to think about the heat that it takes to melt ice. So in this case, I have Q ice, and I know the mass of the ice that I have. I also know the amount in moles that I could have of that ice because I can convert the molar mass of water and my mass to moles. So if I know mass and I know my molar mass, then I can set up and do the first calculation, which gets me moles of water. Once I know my moles of water, I can then use the enthalpy of fusion of ice. That was the last piece of information given in the problem, 6.01 kilojoules per mole. Notice that when I do this calculation, I'm able to cancel my units. My grams cancel with grams, my moles cancel with moles, and I'm left with kilojoules, right? In this case, right, it's not kilojoules per mole, right? It should just be kilojoules, right? So make sure that when you're canceling your units, you're actually canceling to get the correct value of your units. So in this case, it's just kilojoules. This is the amount of heat gained by the ice cube as it melts. When the ice cube has just melted, it absorbed 16.7 kilojoules, and if you need to, you can reference it per mole from the T. That's because the enthalpy of fusion that we refer to is usually kilojoules per mole. But the amount of heat that it takes, 16.7 kilojoules. Now let's think about the next part. So remember that the density of water is 1 gram per milliliter. And we also need to remember that our delta T is our temperature final minus temperature initial. We're going to have to do something with that. We don't know what yet, but that's definitely a piece of information that we need to reference. So if we have our T has heat. And we know that MCS delta T is one of the ways that we can describe that heat. So let's say that we take the energy that it took to melt that ice cube, negative 16,700 joules. Why do I convert it to joules? Because my unit for my specific heat capacity is joules per gram degree Celsius. So I want to make sure that I'm using the correct unit here for joules. I know my mass. I multiply by my specific heat of water. And the only thing that I don't know here is delta T. I'm going to solve for delta T. And then I'm going to take the information from the problem. In this case, I'm going to use my 20 degrees Celsius temperature because that's where my T starts. That's my initial temperature. So my negative 7.98, if I subtract that from 20 degrees Celsius, that means that my final temperature is 12.02. If you're not sure how to set that up, think about it the following way. If I had 12.02 minus 20 degrees Celsius, then I would have a negative 7.98 degrees Celsius temperature change. So the temperature of the T when the ice cube has finished melting. Here's where we have to take a moment and pause and not think so much about calculation, but think about what's actually happening. So when I mix an ice cube and tea, the heat from my tea is getting transferred to my ice cube. That means that my tea is giving off heat and my ice cube is absorbing that heat in order to be able to melt. That's really important because if I'm thinking about the behavior of my system, I need to be able to identify what is my system and what is my surroundings. In this case, my tea is my system, right? My ice, right, is my surroundings. So my system is giving off energy to my ice. Sometimes the way you define your system, right, will allow you to set up and solve a problem, which is not to say you couldn't have defined it the other way. You could have said, well, my system is my ice and my surroundings is my tea, right? But you just have to think then carefully about whether or not you're transferring energy in or out of your system. Okay, so that's the second part. What if we wanted to know the final temperature of the mixture at thermal equilibrium? Now, this might actually be a moment where we have to pause and think about what equilibrium means. Equilibrium does not mean that they have the same, right? It means they're exchanging at the same rate. So when we're thinking about final temperature, we're able to set the heat of one equal to the heat of another because there's a transfer of that heat or energy between them. So my Q of ice is going to be equal to my negative Q of T. My Q of T is negative because, again, that's what's giving off my heat. I know the equation for both, so MCS delta T for my ice and MCS delta T for my T. Do you notice the subscripts that are present there? Sometimes that's really important because you have so much information that you're contending with that you need to be attentive to whether or not it's the mass of your ice or the mass of your tea. And sometimes depending upon the information in the problem, it can be really easy to mix those up. So I highly recommend you use subscripts to help you make sense of the information that is provided in the problem. Notice, when I set up this problem, I'm substituting in my values and I make sure to include my units. It's so tempting to try and do this expediently and exclude the units, but the units are critical because they're actually how I make a determination of whether or not I've set up my problem correctly. So when my units cancel and I'm left with the correct units, say for example, delta T should be degrees Celsius, then I know that I've set up my problem correctly. Again, when you're solving these types of problems, there's several different ways that you can resolve this. For example, you could multiply 50 times 4.184 together and 500 times 4.184 together, and then distribute that to what's in your parentheses. Or you could do it all at once. Just make sure that you are attentive to both your negative sign and making sure that you distribute to all terms. One of the most common errors that we often see folks make is they only distribute part way. So they only distribute to one of the terms and they forget about the second term. So don't forget about the second term. Make sure that you're actually following PEMDAS, so your parentheses, then you multiply and divide, then you add and subtract. Make sure that you are following the correct order in order to be able to get the correct answer. Notice, in this case, I have one term that stays a negative, and then because I'm multiplying a negative by a negative, that becomes a positive. So notice that I have a sign change that occurs here associated with my 25,150 joules. Now, in order to be able to get the correct units, I need to isolate, right, and get my terms by themselves. So I'm going to have 25,150 joules divided by 22,301.2 joules per degree Celsius. Remember the rule of reciprocals? If I have something in the denominator and I divide by that term, it goes into the numerator. So that's why I have the correct units in terms of my final temperature. And again, here, right, I want to make sure that I have the correct sign, right? Both of these are positive, and I should be able to think about, does that make sense? Is my final temperature 10.9 correct? And the answer is yes. If I think about the information from earlier in the problem, right, it makes sense that at my thermal equilibrium, right, that I would be at 10.9 degrees Celsius. So this is an example of a pretty steppy problem if you think about it, right? There's actually multiple pieces that it asks you to solve for, and you could potentially be asked to solve for more, right? If you thought about, say, for example, transitioning from ice to water to gas, you might have to add additional terms as you're doing your calculation. Here's the really beautiful part about problems like this. They're actually pretty straightforward as long as you break them apart and solve them in chunks. Rarely are phase changes the type of problems that you can solve all at once. It's better for you to think strategically and partition them out or solve them portion-wise, where what you're thinking about really, right, is what's happening at each phase, and then what the energy cost is to move between phases. So that's the reason why if we actually take a look at phase change diagrams, it's really important that you're able to read these or make sense of these diagrams. So here's a really great example. We were primarily concerned with moving between solid ice and liquid water. And so if you look here, right, the delta H of fusion, right, is going to be greater than 0 because we're putting energy in order to make these water molecules that now vibrate. When it's ice, they're fixed in place. The hydrogen bonding holds them in a fairly rigid structure. But as we put energy or heat in, now these molecules start to vibrate. If I put even more heat in this case, if I were to have a problem that asked me to convert my liquid water to a gas, right, my delta H of vaporization becomes even greater, right? And so then my molecules are really zooming. Notice, if you're putting heat in, that's the direction where you're moving from solid to liquid to gas. If you were to cool something down, you could go in the opposite direction, right? Here, notice for your condensation, your negative delta H of vaporization is going to be less than 0. If you're freezing, your delta H, your delta fusion, again, is less than 0. And so you should be able to think about your phase changes in terms of whether or not the actual change in enthalpy makes sense. Are you putting heat in or are you taking heat away? What does that do to the molecular structure, right? In the case of ice, right, as I take heat away, my water molecules form much more rigid hydrogen bonds, almost in a lattice or a crystal structure, which is the reason why ice is the solid that it is, and also the reason why it floats, because there's space between these water molecules. Whereas when it's in liquid water, they're crammed together and there's a lot more hydrogen bonds that are forming and breaking between my water molecules. So here's the last picture that I want to show you, right? If we're thinking about phase changes, we can think about cooling, we can think about heating. So cooling steam, condensing that steam, cooling liquid water, supercooling that so that it forms ice, right? This is an example of a phase change that goes in the opposite direction. We've talked about phase changes to warm up water, but it's important that we think about phase changes to cool water too. So both of these are examples of information or knowledge that you're going to be asked about for your final exam part 1 and your final exam part 2. You're going to have to read and interpret diagrams as well as produce calculations. So with that, you're probably wondering, okay, Sloan, how does this all distill? How do I make sense of all of these ideas together? What am I really going to have to do on my final exam? I think sometimes it's valuable to think about the big ideas. In fact, if you were to go back to your concept maps, the ones that you were creating for your learning chemistry workbook, one of the ways to organize information in your concept maps is to think about the big ideas. So here are 6 big ideas that we have talked about this semester that should help guide you as you're solving problems for both your concept inventory, which is the individual assessment for your exam part 1, and for your integrated problem solving, that's part 2 of your exam that you're doing collaboratively with your scientific colleagues. So here's big idea number 1. The chemical elements are building blocks of matter, which can be understood in terms of the arrangement of atoms. So if we think about where that should show up, that's in things like, how do you form molecules, right? What makes up an atom? How do those atoms come together? How can we draw, say for example, a representation of an ion? Big idea 2 is the chemical and physical properties of materials that can be explained by the structure and the arrangement of atoms, ions, or molecules, and the forces between them. So we've talked about intramolecular forces and we've talked about intermolecular forces. It's important that you're able to identify the difference between chemical and physical properties, as well as the way that atoms and ions and molecules are arranged and why there are forces between them. Big idea 3 is that changes in matter involve the rearrangement and or reorganization of atoms and or the transfer of electrons. So when we have a reaction take place, we're either recombining atoms or reorganizing those atoms, or we're transferring electrons between atoms. Big idea number 4 is something that you're going to talk about in a lot more depth in Chem 111, but we did touch on it briefly. And that's the idea that rates of chemical reactions are determined by details of the molecular collisions. So when we think about how crowded an atom is, that might determine how readily it's able to interact with another molecule or atom. Big idea 5, right, is that the laws of thermodynamics describe the role of energy and explain and predict the direction of changes in matter. This is true for the areas that we talked about in terms of exothermic and endothermic reactions, as well as being able to calculate energy and enthalpy. Big idea 6 is that bonds or attractions can be formed and broken, and that these 2 processes are in constant competition. They're going to be sensitive to initial conditions and external forces or changes. So when you're thinking about the big ideas of chemistry, part of what I want you to do is just take a moment, sit back, and reflect on the fact that you actually know a lot of chemistry. If you think about each of the chapters that we have covered thus far in Chem 110, it's a pretty broad introduction to the natural world and the way that chemistry plays a role in everything from biology, right, to physics, the ways that molecules impact environmental science or marine science. In fact, you could make the argument that the chemistry that we've studied is relevant to health science and kinesiology, or the way that our muscles move. And of course, you could certainly see the ways in which the knowledge that you're gaining now equips you to be able to study chemistry and each of those sciences in greater detail next semester. So with that said, we've got just one more thing to do. This is your preview for 1 week left. So today we've reviewed for your final. We've talked about different types of problems and what's going to show up on your individual concept inventory and what's going to show up on your collaborative work. Just to be really clear, you're going to receive part 2 of your final this Wednesday by email from me, and it will be due at midnight on May 11th. That should give you enough time to work on it. So you can work on it on Wednesday, or you can decide to wait until Thursday, or you can decide that you're not going to touch it until the weekend, or you can decide that you're not going to work on it until Monday. It's entirely up to you, and you can make those decisions based on the other responsibilities that you have on your plate. The final part 1 is something that you will need to set aside time on Wednesday during class to do. So from 10 until noon, that exam will be available on iLearn for you. If for some reason you have a time conflict or there's something else that's going on for you on Wednesday and you cannot do it during that time, please email me and let me know as soon as possible, and we will find a time when you can take that exam. So both of these are timed. Granted, the time allotments are different. It's 2 hours for part 1. For part 2, it's a number of days. So you can imagine that the types of problems that you're being asked to solve on each of these exam components is very different. As such, I think it's useful for you to think about how you want to organize your resources and what might be most helpful for you as you're preparing for those final exams.